So today we will see how to generate a 3D far field antenna pattern from 2D cut plane data. There is a Python code that we need to run in order to generate this 3D far field antenna pattern. This is the GUI of the tool. So after we run the Python script, this is how the GUI looks like. Now this code takes in information of 2D cut plane data from two elevation planes. So if you see here, input the DAT files with the elevation patterns. We can also plot comparisons by looking at the plots generated. If the data is too large, there is a downsampling factor that can be entered here. And then the code outputs the FFD file to the folder. Now all the assumptions are written here. What are the units? What are the angles? And the DAT file is basically angle comma gain. So whatever the angle is in that elevation plane, so we have the DAT file in that format. Now in order to generate this DAT file, there can be many sources that the DAT file can be extracted from. Most probable application would actually be using a existing data sheet which only has 2D data and then exporting 3D data from it. For example, we can now see that this is a 2.4 gigahertz compact helical antenna, and generally in our data sheet when we want to incorporate these antennas in our design, we only have the gain data from the 2D cut planes. For example, as you see here, we have three cut planes, and at these three cut planes, we have the data at three different frequencies as well. So in order to incorporate this design into HFSS simulation, we would actually need a complete 3D far field pattern data. So what we will do from this is, when we have any data sheet, first of all, we need to extract the data from this image. For this particular antenna, the XZ and YZ plane would be the two elevation cut planes. We can extract these images by using any snipping tools, or sometimes we can just select images on a PDF and then save image as. So what I've done is I've saved the XZ plane gain and the YZ plane gain as separate images in a folder. Now when we have images with plots, it can be a 2D, it can be a 1D plot like the S parameter plot that was there previously. So this is an efficiency plot, gain plot. We can have 1D plots like this or polar plots like this. There is a tool online which allows to extract data from any different types of plots. So let me open that tool. So this is the tool, the web plot digitizer tool, where we can upload images or PDF documents and then extract the data from that. So right now I have images, so let me choose a file. So I have two files. One is the image XZ and one is the image YZ. So I will input these separately. So first XZ, open. Now this is a polar diagram, so I'll select that it is a polar diagram. First, when we are loading any image into this tool, what we need to do is we need to calibrate, because the digitizer tool will need to understand what is the scale that is there on the image. So we'll go for calibrate. Now if you see, the first angle starts from here, and then we have the 360-degree rotation complete, and this is the gain scale. So here if you see on the right, it asks what type of scale we have. We have a linear scale here for the radial data. Angular is in degrees. So what we will do is, first we'll click on the origin. So this is close to origin. On the right top, you will also be able to see it in zoomed in format so that you can click on the correct location. So this is my origin. Now I'll click on one of the points here, for example, any 2 points. This is P1, and the other one I'll click here. This is P2. Now, if you see P1 and P2, we just need to note down what is the R and theta value at those angles, at those 2 points, P1 and P2. So at P1, R1 would be, if you see here, R1 would be -20. So I'll make it as -20, and at that position theta is 60 degrees. So 7 is written here, but what we can see is 0, 10, 20, 30, 40, 50, and 60. So I can write here 60 degrees. I mean, we can follow the notation according to what we understand. So R2 for P2 is -25, and theta 2 is 10 degrees. Okay, and then we will ask this to calibrate. Okay, so calibration is completely done. Now we need to see from, if we go to the data sheet, we can see that there are 3 plots in each of the images, and the color coding is also mentioned here. I would like to extract the one at let's say 2450. These are overlapped slightly, but we can choose the point separately as well. So I'll try to extract from the green curve, right? This 2450 megahertz. So in order to do that, I can, in the digitizer tool, I can actually select the color that I want to extract the data for. So I can click here, and sorry, yeah, I can click here and then click on the green plot. If you see on the right top, you will be able to see that I'm clicking on that color, and this is my foreground color. Background color is by default generally white or black. So here we will have a background color as white. You can check also what is the background color, which is white. If you have any other image, you can change the background color here. So this is my foreground color for the black trace. On top of it, if we extract data directly now, it will not be correct because we have some overlap here, and especially in this region. So what we can do is we can assign one more mask, noting that this is the data I want to extract. First of all, one mask is the color, the another is the pen mask. So I can set the width of my pen from here and just trace over the data that I want to extract. So this is too wide for the image. So what I can do is I can go to erase and click on erase all, go back to pen, decrease the width slightly, and then trace the highlighter all over the data I want to extract. So if you see wherever there I'm seeing that the data is considerably different for the 3 traces, I'm trying to capture those in this highlight portion. Okay, done. Right now, before extraction, we have one more setting to do. There is this delta x and delta y. So the larger the number, the larger the spacing would be. I need to change it to, let's say, 2 points. I'll change it to 2 points. When I ask it to run, it will extract points like this. If I have 5 and 5, ask it to run. So we will have more spaced out data. Okay. So I'll keep it at 2, delta x and delta y as 2. But here still, if you see, there are some extra points that get generated, right? So in order to do that, in order to actually delete these points and keep only the correct data points, we can have one manual extraction step here. We can delete any point that is not wanted. So click on delete point and just go over these points that are either duplicate or you can delete. Duplicate or, straying away from the ideal data. Okay. So let me just do it for one plot. Now, if the pen width was kept even smaller, we would get much less points anywhere else. The color green is very close to this color of the lines as well. That's why there are some points that are overlaying on the line. Um, so what the pen mask does is help to reduce this extra data points that we may get otherwise. Okay, so this is fairly good enough. I can also, you can add points if you see there is considerable portion where the points are missing. For example, if you see, um, I'll delete one more point before that. Yeah, so you can add a point. So you can just check on the top right section where you see some missing data. If you see, you don't see anything. If you see any missing data, you can immediately add the point there. I don't see any missing data, any considerable difference. So I don't need to add any point. Yeah. Okay, great. So once this is extraction is complete, we can export the data. So you can view the data from here on the left side. Go to view data. So you'll be able to see this is r comma theta format. First, we will sort by theta value. This is the data that we have sorted by theta value, and then export as CSV. So we can download CSV from here. So this is the way we can extract data from images, any type of image. It need not be polar also, even though for this application we need a polar data. Okay, so once this is done, I have actually done this for the YZ plane as well. This is the XZ plane. I've done the same thing for the YZ plane, and I have the two CSV files with me. So I will show those two CSV files as well. So these are the two CSV files, r comma theta files. So I have this for the XZ plane and for the YZ plane that were downloaded from the online digitizer tool. Now we know that the code takes in .dat files, and we need to in that too in the format of theta comma r, not r comma theta. So just need to convert these CSV files into .dat files. There is a code we have done that, convert CSV to dat.py. So when we run this, it will open a location by default. So I can actually go to the pattern conversion folder, select my CSV file. Then it will ask me to where I want to save my dat files. So I already have saved previous files here, but I'll just go example and save. And the second elevation plane also it will ask. I've selected that, and then this is example 1. It has converted to .dat, and which is compatible with our pattern multiplication code. So once the .dat files are generated, I'll just open the .dat file, one of the .dat files as well. So let's see the dat file that got generated. Um, this is one of the DAT files that I had previously saved for the XZ plane. We have now theta comma r. The values are in theta comma r format rather than r theta and in a CSV file. Now this is compatible for our pattern conversion code. This is the pattern conversion code. When I run it, it actually pops up a GUI that I've shown before. So let's run this. This is the GUI that pops up when the code is run. So we can select the two elevation cut planes. Before that, you can also see the gain, scale, angles, and everything. So this DP scale degree, the option was available on the webplot digitizer tool also to select the units and what are the different directions, details about this toolkit. Okay, so for the elevation one, we'll select a DAT file. I'll select the exit DAT file first, open. When I click on open, it plots the data for me in a XY plot. I don't need to close this plot at all. I can go for the selection of elevation 2, which is the YZ. So again, I'll select the DAT file. So it plotted that over the first one. I can click on plot comparisons now. First of all, I can also set the polarization. It is horizontal or vertical. I've set vertical polarization for this antenna. Then plot comparisons. Yeah, this is if I have downsampled, so I've taken all the data points. That's why we didn't really need to downsample as such. And once the plot comparisons are done, we can write the FFD file to disk. So here I will check maybe antenna far field, pattern 3D, and save. So if you see here in the terminal window also, file written is done. So I can close and close the toolkit. So it is completed. This code can be run in any of the Python IDEs. I am using VS Code, but you can use Spider if you want to, whatever you're comfortable with, or PyCharm. So the FFD file that got created, what we'll do is we'll try to import it into HFSS and see how it looks like. So let me open any HFSS window. So I've opened this HFSS window. I'll insert a dummy HFSS project, HFSS design. And in order to visualize, I'll change the solution type to SPR plus, where we can import FFD files and actually see. So right click on 3D components, create antenna, and import file. Once we change the solution type to SPR plus. So here I'll import an external file from pattern conversion. This is what we exported, and finish. So this is the 3D pattern that got generated after from the two 2D cut plane data. The streaks can be improved by uh, maybe exporting for every one delta x delta y from the digitizer tool, but this is a 3D pattern of the helical antenna that got generated after using the code. Thank you.